Hello friends, and welcome to the course of Power Electronics in the Electrical is Easy channel. So today we are going to start with the reverse bias in power diodes. So in the previous video we have seen the use of the drift region, which is the additional part which comes in the power diodes construction. So basically the reverse bias what you see in a signal diode and power diode is more or less the same. The only thing is that the power diodes can have a higher voltage breakdown capability thanks to the drift layer. So we will just start with the reverse bias of power diodes. So under reverse bias, you know that there is only a small leakage current that flows in the reverse direction. That we already know, right? Even when we were talking about normal diodes, we already seen that under the reverse bias condition, only a small current flows in the reverse direction. So mostly this reverse current or the leakage current that flows is due to the minority carriers you have seen during the thermal agitation. The minority carriers can easily cross the barrier potential. This reverse current, we already know, it is independent of the applied reverse voltage, right? It is independent of the applied reverse voltage, but it is sensitive to the junction temperature variation, right? So we already seen that when we were discussing power diodes, not power diodes, the normal diodes. So as the temperature increases, you know that the reverse current also will increase, right? So with these two facts we can draw the graph now. Okay, so this is your current, and this is the voltage applied across the diode. Okay, so VAK. So for example, the basic idea is that you are having a diode here like this. This is a power diode, this is your anode, and this is your cathode. So in the forward bias condition, you know that the anode will be positive with respect to the cathode, right? But in the reverse bias condition, you know that the cathode will be positive with respect to the anode. So here you will have your positive voltage, positive polarity will be here, and here you will have your negative polarity, right? So for the circuit sake, we can just draw a limiting resistor also. So this is a current limiting resistor. So I will put it as RL. Okay, and here is your reverse voltage. So anode is connected to the negative terminal, and cathode is connected to the positive terminal. For the time being, we have taken a DC source here just to show that the anode is negative with respect to the cathode. So you can see that the reverse current is independent of the applied reverse voltage, but it's sensitive to the junction temperature variation. Okay, so let us take a, so basically if this is the applied voltage across the diode, so this side, you know that this is the positive side, right? So when you are applying reverse voltage, your voltage is in the negative side, right? Because VAK is positive, is in this direction. So when VAK is negative, which is in case of the reverse bias condition, that will be in the left side here. Okay, so whatever your voltage you are applying, whatever the voltage you are applying in the reverse direction, the reverse current will be exactly the same. So I can draw something like this, right? Something like this I can draw, right? So whatever is the voltage, you can see that this is minus VAK. So whatever the voltage of VAK here, let it for this value or this value or this value or this value, you can see that the reverse current is exactly the same. Okay, but it is only changing with respect to temperature. Okay, so let us take two temperatures now, one TJ1, okay, and one TJ2. So TJ1 is the junction temperature of the diode. TJ2 is also a junction temperature of the diode. For two cases we are taking, and let us assume that the TJ2 is greater than TJ1. Okay, so we will draw the TJ2 graph also here. So since TJ2 is greater than TJ1, temperature of junction second condition is greater than the temperature of the first condition. For example, the saturation current for the second case will be greater than the saturation current for the first case. So this is the saturation current for the first case. The red one is the IS1, and I will draw a green graph which will be IS2. Naturally, you know that since the junction temperature of the second case is higher than the junction temperature of the first case, the second saturation current will be higher than the first case. So that will look something like this. Okay, so for the same voltages, for the same reverse voltages, you can see the value of the saturation current is higher, and that we already seen, because naturally when temperature increases, you are having more and more thermally excited electrons which can be part of this reverse conduction process. That is the basic idea. Now when the applied voltage reaches the breakdown voltage. Okay, so we'll keep some point here which is called the breakdown voltage point. So for example, this point is the breakdown voltage. This is the breakdown voltage. Let us take for the first case Tj1 here. So when the applied voltage comes almost nearer to the breakdown voltage, what happens? So when the applied voltage reaches the breakdown voltage, the reverse current increases due to impact ionization and consequent avalanche multiplication. That we have already seen in the previous videos, right? When you are applying more and more reverse voltage, there is this process which is called impact ionization, and due to this impact ionization, more and more electrons will be, more and more charge carriers will be free for conduction process, and this process is called avalanche multiplication, and a large current can flow in the reverse direction. So as we approach this particular value of VBD, let us take for the first case, the current will start increasing, and at the particular point of VBD, it will go into avalanche breakdown. So at this particular point, you can see the diode is going into an avalanche breakdown here. Now, when you are having higher temperature, what is the condition? See, you can see that the voltage does not increase further. Although you are trying to increase the reverse voltage, the voltage across the device does not increase any further, and the reverse current is limited by this external circuit. So this RL which I have shown, that is the external circuit. For example, this reverse current now will be equal to I is equal to V divided by RL. Okay, so for example, that is this value here, the reverse direction. So I is equal to V divided by RL in the reverse direction. Remember that this is in the reverse direction. The reverse current will be limited by the value of the external circuit which is connected to the diode. The basic idea of a reverse bias in the power diodes. Now, when you are having a large current which is flowing in the reverse direction, there is excessive power loss. Okay, there is excessive power loss, and also there will be increase in the junction temperature. And if you continuously work the diode in this reverse breakdown region, two things are happening. One, power loss is increasing, and due to the power loss, the junction temperature is also increasing. So this is like a cycle, right? So it's like a cycle. So junction temperature increases, more current will flow. More current will flow, more power loss will happen. That power loss will further increase the junction temperature. So this junction temperature, so this power loss and the junction temperature are like a cycle. And once this cycle starts, it will quickly destroy the diode. Therefore, you don't want to operate the diode in the breakdown region for a long time. The diode is not rated to operate in the breakdown region for a long time. So continuous operation in the reverse breakdown region should be avoided. So the continuous operation in the breakdown region should be avoided. Okay, so that is the basic idea here. Now, in the reverse bias condition, of the diode, there are some very important terms that you have to know. And usually in the data sheets also you will find these terms, and also in some numericals also you might find that these terms are being used. Anyway, in future if somebody is going to be working in the field of power electronics, they have to understand all these terms if they want to select a particular device for a particular equipment. Okay, so that is the basic idea of understanding these important terms. First is the DC blocking voltage or DC VRDC. Okay, so this is VRDC. This is the first term that we are going to see. So what is the definition? This, I'll just take a different color now. Yeah. So this is the maximum direct voltage. Remember, it's a DC value. Maximum direct voltage that can be applied in the reverse direction of the device for an indefinite period of time. Okay, so this is basically a reverse voltage that you can apply across a diode for indefinite time. So whatever you can apply it continuously on the diode, and the diode will not get damaged. Okay, so the basic idea here is that you are having a diode. Okay, you are having a diode here, and if you are applying, this is the anode, this is the cathode, so you are applying a reverse voltage of VRDC. Okay, so this is the maximum voltage that you can apply across the diode for an indefinite period of time. This indefinite period of time is very important. Okay, now why this term is important? This term is basically useful in selecting diodes for DC to DC choppers and DC to AC voltage source inverter circuits. Some of these terms you might not be able to understand now, but however, when we go through all these topics and you come back here, you will be able to understand these things properly. Anyway, for the time being, you should just remember that this is useful. This term is useful in selecting diodes for DC to DC choppers and DC to AC voltage source inverter circuits. Okay. Now, next is, then second term is the RMS reverse voltage. RMS reverse voltage or VRMS. Now remember, all these quantities are reverse bias condition quantities. All are reverse voltages. Remember that. So this is the RMS value of the power frequency sine wave. Okay, the power frequency sine wave voltage that can be directly applied across the device. Okay, so this is an RMS value. So you had a DC value in the previous place. You had that VRDC. So that was a DC value. Okay, so the corresponding AC value is called VRMS. This is the RMS value of the power frequency sine wave. You know that the power frequency sine wave, how does it look like? This is the sine wave, right? So it basically tells you the RMS value of the power frequency sine wave that can be applied directly across the device. Okay, so if you take the RMS value of this reverse voltage side, you will be able to get this value. Okay, so this also will not damage the diode. So you know that diodes are used in AC to DC rectifier circuit. Some of you might have learned already it in your 12th class. So this particular parameter, that is RMS reverse voltage, is useful in selecting diodes for AC to DC rectifiers. I hope I am clear here. Now the third term is not the third. There are two more points that we have to see. So usually the manufacturers, while giving this value, they assume that the supply voltage will rise to a maximum of 10%. So if you see, for example, we are having 230 volt RMS, right? In our country, we are having 230 volt RMS. But if you see this value, which is supplied by the manufacturer, it will be a little bit higher as compared to 230 volt. So they assume that there will be a variation of a maximum of 10% for this particular rating. So when we see the forward characteristics of also the diode, we will see some data sheets. In that data sheets, you can clearly see this rating will be a little bit higher than the 230 volt RMS that we are normally used to. And also this voltage, this RMS reverse voltage rating is different for the resistive and capacitive loads. Based on the loads also, the manufacturers will specify different voltage ratings. Now the next term is a little bit important. The next term is the peak repetitive reverse voltage, or it is also called as VRRM. Peak repetitive reverse voltage. So till now we first saw VRDC, it is a DC value. Then we saw the RMS value, right? We saw the RMS value. So you know that RMS value is also an equivalent DC value, right? For the same heating effect. Now we are seeing instantaneous value. Now we are not seeing RMS value. Now we are seeing instantaneous value. Now usually a diode, for example, this is your input voltage waveform. The diode might be subjected to reverse voltages, right? For depending upon the circuit, the diode might be subjected to the reverse voltages. So it is the maximum permissible value of instantaneous reverse voltage appearing periodically across the device. That means throughout the working of that particular circuit, a particular reverse voltage will continuously come across the diode. So that is the meaning of this voltage appearing periodically. It is not a once in a time event. Okay, it will continuously happen throughout the work till how much time that circuit is working. During a particular interval, continuously this reverse voltage will appear. For example, you can look at this waveform. So if this voltage is continuously appearing across a diode as a reverse voltage, so you will see that that value is the peak repetitive reverse voltage. Now usually when you see the commutation circuits, you will see that the input voltage has a small change, like it will be like this. Okay, something like this. You will learn about this later. So you can see that this reverse voltage is a little bit higher than this sine wave. This reverse voltage is a little bit higher than this sine wave. So in that case, the diode manufacturer will consider all these things, and this will be your peak repetitive reverse voltage. You can see that this value is also repeating throughout. Now where it is used? I told you this appears during commutation in a converter. So usually you can see that it is not this value that we take, it is this is the peak value. See, this is the peak value. Appears during commutation in a converter. This term also you might not be knowing now. In DC motors you might have seen this commutation term, but of course in power electronics also we will see in the future lectures. Now the next important term is the peak non-repetitive reverse voltage. In the previous we have seen VRDC, DC voltage which can be applied indefinitely in the reverse condition. Then we saw VRMS, RMS value of the sine wave that can be applied across the diode in the reverse condition. Then we saw VRRM, right? This was the peak reverse voltage, instantaneous voltage which can be applied, which appears periodically, right? It is appearing periodically, but sometimes in the diode, especially during switching conditions, there might be a very high voltage which is going to come across the diode in the reverse condition, especially during power line switching using circuit breakers or a lightning surge which is coming. There will be a very high voltage. So that voltage is not repetitive. It is different from this VRM. It happens very rarely. That much diode can withstand. But if that voltage continuously is applied across the diode will fail naturally. Okay. So peak non-repetitive reverse voltage, VRSM, is the maximum allowable permissible value of instantaneous reverse voltage. This is also instantaneous value appearing across the device. And what is the important term? And this must not reoccur. Okay, this must not reoccur. So what happens is that, for example, this is your input voltage waveform. Okay, suddenly at some point, for example, see, remember, for some diodes, depending upon the circuits, this area can be reverse voltage. And if you already seen full wave rectifiers, etc., for some cases, this might be reverse voltage. Okay, so that depends upon the circuit. So for example, there is some kind of a switching happening here and a huge voltage comes like this. An abrupt voltage comes like this. So manufacturers will give you a rating for this value also. So beyond this value, the diode will get damaged. But once in a while, if such a value comes, diode can survive. And what is that maximum value that can come? That is peak non-repetitive reverse voltage. So where it is generated, it is either generated by power line switching, that is usually the opening or closing of circuit breakers, opening and closing of circuit breakers, or lightning surges, Now we have seen all these important terms. I told you we'll see some data sheets in the later part of the course when we complete the forward biasing area also. So we'll just draw a reverse characteristic now. So this is your voltage, this is your current and this is your voltage, and let me just draw one simple characteristic like this. Okay. So you know at this point the diode has completely breakdown, right? So this is your VBD, or some people in some books you can call it as VB also. This is your breakdown voltage. So first term was VRDC, right? The first term was VRDC. It is the maximum value of direct voltage that you can apply in the reverse direction for an indefinite period of time. So we will take that value somewhere around here. If you see quantify these values, you will find a graph like this. So this might be your VRDC. And another interesting term that we can put in this graph is VRRM, right? It was the peak repetitive reverse voltage. Okay, it is the peak repetitive reverse voltage. Remember this thing. I showed you it's a peak repetitive reverse voltage. So that I will put somewhere around here. This is an instantaneous value. Remember that. So this is VRRM. Okay. So the next term that we can put in this particular graph is peak non-repetitive reverse voltage. Okay, I told you this usually comes during the opening and closing of circuit breakers or during lightning surges. That value will be higher than this VRRM value. See, this value is the VRRM value, right? This is the VRRM value, and this value I'll just put it a little bit higher here. So this value is your VRSM. Okay, so that will be higher than VRRM. So I'll put it somewhere around here. VRSM. Okay, and beyond that you naturally have your If the voltage is so high, the diode goes into breakdown region. Naturally, the diode will fail beyond this particular point here. Okay. So today, basically, we have learned some important terms. One, we have seen the reverse bias condition. It is very similar to what you see in the normal diodes. The only thing is that it has higher reverse breakdown capabilities. Okay. Then you have seen some important terms. In fact, this lecture is more of that important terms. So the important terms that you saw, that was, first one was VRDC, maximum allowable reverse DC voltage that can be applied for indefinite period of time, right? Indefinite period of time, indefinite time. So whatever be the how much ever time you apply, the diode is not going to get damaged. Then we saw VRMS, right? This was the RMS value of the sine wave. RMS value of the sine wave that can be applied in the reverse direction and the diode will not fail. Then we saw VRRM, right? So this was the instantaneous peak value, maximum instantaneous peak value, which comes across the particular diode. So this was the RMS value and this is the maximum instantaneous peak value that can come across the diode, especially during the commutation process. Finally, we saw and this occurs periodically, right? This occurs periodically. That means throughout the working period of the diode, this value will come. But however, we then finally saw VRSM. This is mainly due to lightning surges or switching. So for that also you are having a maximum value, but this cannot continuously happen. In that case, you will have to see what the problem in the circuit is. This cannot continuously happen, but the manufacturers give a particular value for that also. So in the next video, we will start with the forward biasing process, and we will see some important terms associated with the forward biasing process also of the diode. Okay. So till I see you in the next video, it's me Varun signing off and have a great day. Thank you.
Now that the video is over, please stay with me for 30 more seconds. Now the vision of this channel is to create a repository of good quality videos with crystal clear explanation regarding various topics related to electrical engineering. Now if you want to help me spread the word, please share this video with anyone interested in these topics. The second thing is that for me, education is a two-way process. Therefore, if you have any doubts or suggestions regarding any of the videos or regarding the channel, please put them in the comments below. We can have a healthy discussion and that way we can build a strong community of electrical engineers. So that's it for today's video. So till I see you in the next time, it's me Varun signing off and have a great day. Thank you.